Hey everyone, and welcome. Have you ever stopped to think about how that's even possible? You know, how a simple word you type or a button you click can make a computer do, well, pretty much anything. It seriously feels like magic, but it's not. It's actually a conversation. And today, we're going to pull back the curtain and show you exactly how that conversation works.
So here's the big question, right? How do our thoughts, our complex human ideas, get translated into something a computer can actually understand and act on? It's a huge communication challenge. It's kind of like trying to have a deep conversation with someone who speaks a completely, and I mean completely different language.
All right, so here's our game plan. First, we're going to tackle that basic communication gap. Then, we'll get into the special languages we invented to bridge it. After that, we'll meet the great translators that do all the heavy lifting. We're even going to peek inside the machine's mind, then see how this all fits into building a real app. And finally, we'll ask a really important question. What actually makes code good? At the end of the day, programming is really all about one thing: bridging a massive communication gap. See, we think in abstract ideas, in stories, with all sorts of nuance. But computers? Nope. They think in pure, simple, do this, then do that instructions. There's no room for maybe. And that set of instructions? That's what we call a computer program. I love this analogy. Think of a programmer as a manager, and the computer is their team. The program is just a super specific list of duties. The computer doesn't get creative, it doesn't improvise, it just follows that list of instructions, step by step, exactly as it's told.
So how do we actually write these instructions? I mean, we can't just write them in plain English. We need a special language, one with a very strict vocabulary and grammar rules. And that's exactly what programming languages are.
And you know, not all of these languages are the same. On one hand, you've got high-level languages, things like Python or Java. They're designed to be closer to how we think. They let us focus on the logic of our problem, not the nitty-gritty of the hardware. But on the other end, you have low-level languages. These are way closer to the machine itself. They're tougher to work with, but they give a programmer incredible control over the hardware. Okay, this leads us to two words you absolutely have to know: source and object. The language we write in, like Python, is the source language. But the language the computer actually understands, that raw code of zeros and ones, that's the object language, which is also called machine code. So the whole game is about getting from source to object.
So how do we make that jump? Well, we don't do it ourselves, thank goodness. That's where the translators come in. These are actually special programs themselves, and their entire job is to convert our human-friendly source code into the machine code the computer can execute. Now, the two main types of translators are compilers and interpreters, and they have totally different styles. A compiler, it takes your entire program, the whole thing, and translates it all at once. An interpreter, on the other hand, works one line at a time. And this one difference changes everything, from how fast the code runs to how you find errors.
To make this super clear, think of a compiler like a book translator. They take the whole book, right? They translate it from page 1 to the very end, and only then do they give you the finished translated copy. The key is, you can't read a single sentence until the entire job is done.
An interpreter? That's a completely different beast. It's more like a live translator at the UN. They listen to one sentence, translate it immediately. Listen to the next, translate it. It's a real-time back-and-forth process. This is actually why languages like Python feel so interactive and immediate. They're often using an interpreter behind the scenes.
Okay, so we've got our translators doing their job, but what happens next? What does that code actually look like as it gets closer and closer to the processor itself? Let's peel back one final layer.
Right above the raw binary code, you'll find something called assembly language. It's still super low level. I mean, it's tied directly to the computer's hardware, but instead of just zeros and ones, it uses these short, human-readable words called mnemonics. And yep, it needs its own little translator, called an assembler, to make that final leap to machine code.
And here it is, the bottom of the rabbit hole. Machine language. This is the computer's true native tongue. It's nothing but a stream of zeros and ones that the central processing unit, the CPU, can understand directly. Every single program, I don't care if it was written in Python, C++, whatever, it all has to become this to actually run.
Whew, okay. We went deep into the machine there for a second. Let's zoom all the way back out. Because writing code, it isn't just about translating languages. It's one part of a much bigger, much more organized process for building real software.
And this, right here, is the program development lifecycle. And this might be one of the biggest takeaways today. Just look, where is coding? It's step number 4. A ton of work happens before you write a single line of code. First, you have to really understand and analyze the problem. Then you design a solution, maybe with a flowchart, and you map out the logic. Then you code, and you're still not done. After that comes compiling and debugging, testing it, deploying it, and finally, documenting and maintaining it for the long run. It's a real engineering process.
Now, I mentioned mapping out the logic. That's an algorithm. And honestly, the best way to think about an algorithm is just a recipe. It's a very specific step-by-step procedure for solving one particular problem. And just like a good recipe, every single step has to be crystal clear.
Let's look at a super simple example to make this real. Say your problem is find the larger of two numbers. Well, the algorithm, the recipe, is pretty straightforward. You start, you get the two numbers, A and B, you compare them, you put the bigger one into a variable, let's call it lar. Then you show the result, and you stop. That's it. It's that kind of clear, logical thinking that has to happen before the coding even starts.
All right, last thing. Let's say you've done all that. Your program runs, there are no errors. You're done, right? Well, not so fast. Because just getting a program to work isn't the finish line. Professionals strive to write good code, and that means a whole lot more. So what makes a program good? Well, for starters, it has to be readable. That means another human being can look at it and actually understand what's going on. It's got to be efficient, using as little memory and processor time as it can. Good code is portable, so it can run on different kinds of computers. It's flexible, so it can be changed later without falling apart. And it's well documented, so other people know how to use it and work on it. It's all about building something that isn't just functional, but also strong, clean, and built to last. So there you have it. We've seen how a simple idea travels through a translator deep into the mind of a machine and comes out the other side as a real action. We've learned that code is so much more than just instructions. It's a disciplined, creative way to communicate. It's a language that we literally use to build entire worlds inside our devices. Which leaves just one question, really. What are we going to build with it next?